The whiskers are now a standard error of that estimate, and you'll notice I've avoided doing it here, or if you'd like, I'm doing the naive one of just 0, because I don't know how to draw standard errors for things that are 0 anyway. But the idea here is that, if you remember, some of these were more stable than the others in the exact confidence interval thing. The Bayes posterior mean, or the posterior mean, shrinks things towards some common value, and for SMRs, the common value is automatically forced to be 1, or at least close to it. And you get the thing that happens in Bayesian procedures in general, and it says, if you have a highly stable or a relatively stable estimate, leave it alone. Doesn't need any help. But if you have highly variable ones, like this whisker out here, it's almost purely variance, and shrink it back towards the common value. And you can think of this as nothing more than another way of trading off variance and bias to get good mean squared error on estimates. It's really no different in nature from deciding whether or not to put another regressor in. So you can kind of make this aphilosophic, and you can also say there are lots of mathematical theorems, lots of simulations, and lots of real-life examples to show that these estimates are just a lot better at almost any purpose you can think of. But they also show something else, and that is if you're ranking, these lines cross. And so the order here is very different from the order here, and if you were choosing between them, well, let's put it this way, there's something to choose between them. Which to choose if you were forced to? Well, if I were forced to, I'd do this, but I'd rather go back and say, I'm trying to rank. I'm not necessarily trying to estimate the log SMRs. So why don't I actually take the ranking goal right from the beginning and see where it leads you? So those posterior means are more condensed, and here's that same plot as I had with the exact confidence intervals, but now I've just done it with the dots are the posterior means and the bars are the Bayes posterior intervals. And you may say, well, Tom is a lousy plotter. And I actually don't know what happened, why this migrated up here, but why doesn't he use the whole scale? Because what I wanted to do is use the original scale that I had before and show how shrunken things are. But then I'll be a better plotter guy and do it this way. So one thing you notice, and it's the reason that posterior means don't work poorly, at least, is that the posterior uncertainty of these things used to be very, very different for these units. One of the things that the Bayes posterior does, just as a consequence, is try to flatten that uncertainty. And so we're now in a situation where the uncertainty is very similar, and actually ranking these isn't so bad. It's not perfect, but it's an interesting phenomenon of Bayesian things that it stabilizes the uncertain ones, it doesn't do so much for the others, and it kind of balances the books amongst things. Well, here's to me the beauty of the hierarchical and the Bayesian structuring is, if I want to go after especially a non-standard goal, in this case like ranking, I can do the following thought process. I can say, what if I actually knew these SMRs or these log SMRs, and I wanted to rank them? Nobody can force me to want to, but let's say I wanted to rank them. What does that mean? Well, your collaborator may not be able to write this down, but hopefully you can, that it means I'm going to sum up the indicator functions about theta 1 being greater than theta 2 and so on and so forth. And if I put the or equals part in here, then the smallest theta is going to be greater than or equal to itself, and we'll get rank 1, and the others will get what they get. So my goal isn't to estimate the thetas, for this goal at least, it's to estimate R of theta. It's a very nonlinear function, it's a step function kind of thing. But in principle, if I have the posterior distribution for all of these thetas, I also have the posterior distribution for all of these, and I can have the goal of do something good with it. And so I'm giving the kind of easiest example here is, let's go for what's squared error loss, not of the thetas, but of the ranks. And as with everything else in life, squared error is optimized by expectations. So what I really want to do is compute the posterior expected rank. And that's just summing up not the indicator functions anymore, but the posterior probability of thetas exceeding each other. A very different computation from producing the posterior means of the thetas and ranking those. It's really doing all of this in the ranking land. These numbers can then be made in this to be percentiles just so it sits in 0, 1 by this kind of a computation. And quite dramatically, these numbers are not, if you had 100 units, these are not ranging from 1 to 100 like the ranks really would. They're also shrunken. They may start at 15 and only go to 83, and the jumps might be like 15 and 15.02 or something like that. A strong message that we don't have a lot of information there. If you really want ranks, you can force the ranking as these, and so instead of R bar, I call these R hat, which is simply saying rank what you got there and you can show that's optimal. It hides completely the fact that these R bars may be very close, these P bars are very close. It just says go 1, 2, 3, 4, 5 because I want it. But the main point is I've now directly addressed the ranking goal, and we'll get to another mode of addressing it too, but the technology has allowed me to first of all say the hard question. What would I really want to do if I had these thetas in my hand without any uncertainty at all? Frequently that's the hardest question for anybody to answer in an applied problem, but here if I say we're going to rank, we can write that out mathematically, and at least all we need is the laws of probability to tell us what to do, and sometimes it's hard work to do it, but you know what you want to do. Okay, so a little simulation result that I'll spend a little bit of time on trying to explain. Its performance of this ranking procedure for squared error loss of the ranks. In other words, how close are you on average? You may or may not think that's the greatest criterion, but just to give you a feel for what's going on. And I'm doing it with 3 scenarios. One is, this is the ratio of the largest variance to the smallest variance, all of this being where the thetas are normal. If all the sampling variances are the same, then all procedures produce the same ranks. You can rank the MLEs and you'll get the same answer as ranking the posterior means, and you'll get the same ranking as doing the thing I just did on the previous page. And so if you look at the simulated typical squared error loss, when all the units are both symmetric and equally variable, it doesn't matter what you do. And what are the things I'm doing? I'm doing these optimal percentiles. I'm doing the posterior mean of the log SMRs. This is, don't even worry about the formula, but it's the posterior mean of the SMR itself. It's really just an expectation of a log normal. But theta is the log of this, but you can see that you get the slightly different formula. And this is just ranking the MLEs themselves as opposed to the posterior means or the optimal thing. They all give 516. And it's worth kind of knowing that this is better than knowing nothing, and it has to do with how much information is in the system. Let's just jump to the case where the largest variance is 100 times the smallest one, and the progression here is that you have variances that go in a log equal or a geometric series from smallest to largest. So this is like highly variable variances. And you pay a little penalty in the sense that for units that have differential variance, you can't do quite as well as you do when they're all completely comparable. So here's the optimal performance under squared error loss. Posterior means of the thetas still aren't bad because they're balancing the books on those variances pretty well. So one would never care about this difference really. But now if you instead had taken the SMRs themselves as your object of interest and done posterior means of those, you get notably degraded performance, where we all know that if we're ranking, it shouldn't matter whether we're ranking the SMRs or the log SMRs or any other monotone transform. The ranks are the ranks are the ranks are the ranks. So you really want something that, if nothing else, doesn't get affected by the monotone transform. If you go to just using the Ys, which is really the MLEs that are these noisy objects, you pay a big penalty. So this example, it's one of many, but it really shows that once you get to the point of the variability of the units being different, and this is a general statement, but here it's done just for the Gaussian distribution, it's really important to go after the right trade-off, basically. And so you're paying a big penalty by certainly ranking these. A small one here, but if you weren't smart enough to know that you should transform to get things to be reasonably Gaussian, you might be doing this one, and there's a fairly big penalty there. And of course, I could come up with 8 million scenarios that produce things. Now, just so I can tell you, This GMV is 1. This is a hierarchical model where the prior variance for the thetas is 1. And here's a case where the typical sample variance is 1. So that in the Gaussian world, you're doing a 1/2 weighting of prior and sample. That's what this geometric mean of the variances is. And for all of these cases, even the 100 case, the geometric mean of the variances is still 1. So the typical variance is still 1, but they're spread out. If I made the geometric variance here really small, I'm getting more y's are almost like the thetas. I'll get much better performance, much smaller numbers here. But this is just one example. Taking those same things and looking at what you might call a traditional display of uncertainty, there are 4 panels here where the vertical plot is exactly the same in all of them. It's the optimal posterior mean of the percentiles. And it's hard to see here, but it's the p-bar, so it's the ones that don't necessarily fill out the full range. And the 4 different x-axes, or whatever you want to call them, are, here's the optimal one in the sense of discrete rank. So these are just produced by ranking these. It's not a big surprise that things are monotone. They have to be. This is the one I've got to make sure to remind myself. This is the posterior mean of the SMRs. This one are the Y's, or the MLEs, and this one are the Z's, which are the hypothesis testing. And the more you see non-monotonicity here, the more you know that these are degraded performance compared to the one that should be used. I think the main message here, though, is not so much the jumping around of these dots, but the main message is that whatever these ranks are, they sit in a sea of uncertainty. That these are confidence intervals for the, let's go to the one that's easy to look at. And so, yeah, you might be able to tell that this dialysis center is actually one that is way down here, but pretty much the main message is we don't know anything, even for the optimal one. And so this picture of uncertainty, I think, is as important as anything here. One more example, which I can promise you I didn't search for to make this happen, when you see what I mean by the this, but it's an impressive this. This is another example where the analysis is dealing with length of stay. It's again a health services example. For many hospitals, there's so much data that the MLEs are actually so accurate that in fact there's no Bayes action and everything is fine. But just to show a pedagogic thing, we'll take a 10% sample that makes things have enough action to them. So it's a bit of a cheat. This is a case where there's actually a regression structure in the prior with 2 covariates being adjusted for, and so what we're looking for is it's like an SMR in that it's the residual after having adjusted for the reason for stay and the comorbidity status. And it's another one with incredibly discrepant standard errors or variances. And that's true even if we did the full sample, you still get these kinds of ratios. So the least squares mean adjusted population typical length of stay is 14.5 days. And the estimated variability of that length of stay in the sense of what is unaccounted for by these covariates, but is true variation in hospital to hospital truth, is that there's about a 3.1 standard deviation, so that you could imagine that for the hospitals in this framework, plus or minus 6.2 days would not be unusual even after having adjusted for this, and not because of sampling variance, just it's unexplained. The usual, if you'd like, random effects model. So you can think of this as the prior, and you can think of this, prior mean, and this is the